right. So we have reached the end of Unit 2, which is, so we basically covered the genetic algorithms. We covered kind of extending genetic algorithms to kind of this more almost computational creativity and cybersecurity and artificial immune systems and such. And so now, so because we've ended that unit, I put a little auto-graded homework on Canvas that goes over some of those concepts and asks you to skim through 2 of the readings that are associated with it and answer just a couple of quick questions about that. So that's online, and I think I've got to do in like a week from Sunday or something, maybe a little longer than that. I think that's I felt like I 17th. I think the goal was like not the next Sunday, but the Sunday after that. I think that was my goal. So now we're flipping into a new section. So let me make sure I don't go off script here. All right, so now I'll call this Lecture 3A. And we're moving in now to this, I think an area that I think is really well suited for evolutionary algorithms, multi-objective optimization algorithms, which sort of fits within the broader category of multi-criteria decision-making. Or analysis, sometimes shortened to MCDM or MCDA. And it's basically, when I have the same spirit of optimization, but I have conflicting criteria. So I have a problem that requires me to make a decision, and I have conflicting criteria. So DM being decision making there. And so one example of this, especially if we're trying to think of population-based things, is things that can be modeled in terms of game theory. So this is a small subset of this comes from the field of game theory, where the idea here is that I consider a model. So consider having multiple so-called players. So each player, let's call player 1, has some objective important to itself, I'll call a utility function, that has various, they're actually, you can think of them as decision variables, but player 1 only has access to one. So there's this U1 is the benefit to player 1, but player 1 really only has control over X1. And in general, X1 can be a vector, and control over multiple things, but there's a bunch of components that they don't have control over that other players will have control over. And so in economics, when we talk about utilitarian, so we talk about different ethics. And so in economics, we have consequentialism, which is we focus more on the ends and not the means. And in the ends case, we quantify that by thinking of every person in society as a utility, and we are looking for an economic allocation that brings kind of the best overall utility to a group of people. And then we have to define what we mean by best. And so that's the utilitarianism is a subset of consequentialism, where we can define these utilities and come up with certain ways to aggregate these utilities. But we can think of this sort of more generally in terms of game theory. We've got multiple players, player 1, player 2, you can view them as members of a society, you can view them as robots that have no communication with each other and yet still impact each other. That's another way to view it. So player 2, similarly, will have a utility function, and it will have the same structure, but in her utility function, she doesn't control this aspect of it, she controls this aspect. And so she's stuck with whatever everybody else does here, and her benefit might be different than this benefit. So these might be different functions, but all of the functions are potentially affected by the decisions of all the other players. And you go all the way up to player N that has player N's utility function, and player N only has access to that one there. Now, as a matter of notation, rather than me circling these things, very often we write these utility functions with this notation. I might say ui xi comma x minus I. And you can kind of think of this, especially when these are vectors, as I'm saying these are the variables that player I controls, and these are all the other variables that player I doesn't control. And that's just the notation, what we mean by minus I. So it just makes it easier for me to not write something as cumbersome as this, even though it kind of changes the sort order. And so in game theory, one of the equilibrium notions we have is the so-called Nash equilibrium. And so again, I'm couching this in terms of multi-criteria decision making. In other words, the idea would be is, what is a useful way to think about a solution to a problem in which you have multiple players with different reward functions that have different control over each one's reward functions. And so the Nash equilibrium was one way to think of that. And the thought here was that this is an equilibrium concept where we can say for all I and all xi, then we are at an equilibrium, which I'll call x star, that is such that the utility, if I were to keep, so I've got xi star, x minus I star, is greater than or equal to the utility of a different xi and the same x minus I star. And so notice the difference here. And this here is viewed as a no regret condition. So I'm not using regret in the sort of multi-arm bandit sense for those of you in machine learning, but it's just kind of a more general idea that if I'm at the equilibrium, if everyone else stays at the equilibrium, I will not regret keeping my choice. There won't be another nearby choice that I can choose that will end up doing better so long as everyone else keeps doing what they're doing. This doesn't mean it's going to be best for everybody. It could be that if these players got together, they could all agree on certain plays that would benefit them all more than the Nash would. But given that they can't coordinate, then this is sort of saying, given that everyone else is going to do what they're going to do, then I am going to be happy enough staying here. So, yeah.
The x minus I remains the same in the both?
Yeah, this is the same in both of these sort of things. That's the idea, is that all the other players keep playing the Nash. And the question is there a better strategy than Nash for me to play? And this is saying if all the other players keep playing the Nash, there is no better thing for me to do. I should just keep playing the Nash.
But the x's are changing, right? Like xi is different on either sides, only x minus I is the same.
Yeah, this is the only one that's the same. These here, the other players are the same. And we're saying that that for all, so that's the for all, so I'm saying for all, that's what I mean by this here. So for every player and for every other option that each player could make, then the Nash is the best thing that player can do, given that none of the other players are changing what they're doing. So for player I, if player J is forced to continue playing the Nash, then player I should continue to play the Nash, because if player I changes and player J doesn't, then it's not going to be better for player I. Yeah.
Maybe it's just because I'm not seeing where this is going for a practical example, but it just seems like it'd be a very rare case where people wouldn't, or agents in this case, wouldn't change their behavior.
Well, that's the point of the Nash equilibrium, is that you're saying that given that there is no way for players to coordinate, then the idea would be, how can I describe the likely outcome of that group kind of playing in the same sandbox? And given that these two players can't coordinate, I can't count on that player doing anything good that's for me. So I have to kind of do what's best for me, given that nobody else is going to be looking out for me. And so this is saying, then what is that strategy that everything will shake out to be? And that's what the Nash is. The Nash is saying that I could do better. If I could just get this idiot to do something else, we both could do better, maybe at the cost of everybody else. But given that I can't coordinate with that other idiot, then I'm stuck doing whatever I can just by myself. And this is why Nash optimal solutions show up in high performance computing and parallel numerical processing when you don't have, so when we talk about, when we go to distributed algorithms where you do not have much coordination among computing agents, where they don't communicate very much, if you want them to run as fast as possible, then very often you'll find that it's easiest for them to converge to a Nash. So mathematically, then you ask, what would be the Nash if I didn't have them communicate? And then you see what they settle out to be, and if that's a good solution, better than, even if it's not quite the best, but it's not that bad, then you'd say, all right, I'm just gonna have them all climb gradients and solve this Nash. I'll get to that in a second. I'm getting kind of a little bit ahead of myself. But that's the idea behind a Nash equilibrium. It is the best you could do, given that you can't control anybody else.
So
Yeah.
you can think of it as a heuristic. So you're basically simplifying the problem a little bit, given that nobody's communicating, and then getting a solution.
Well, I'd be careful in calling it a heuristic, because this is, when we have, I guess what I'm trying to drive at here is when you have multiple objectives, it's not clear what optimum means. And this is one notion of optimality. Are we at the Nash? Now you can say if we're not at the Nash, then the question is like, that might tell you is that if we're not at the Nash, then maybe there's actually some side playing going on between these players, or maybe we're on the way to the Nash. But this is sort of suggesting that if all these players are truly independent, then this is the notion of optimality that we have. Yeah.
You told that both the I's are different, right? In the utility function.
Well, I mean, all of these, like,
Yeah.
they're all the same across this expression.
Okay. Yeah,
So for every player, this will be the case simultaneously, for player one, for player two, etc. So no one is tempted to change what they're doing. The only reason you'd ever want to change is if you could manage to get someone else to change. But if you can't get them to change, then you are better off staying at the Nash. That's the idea of a Nash equilibrium. A Nash equilibrium may not exist, or it may exist, but it may not be unique. There might be multiple Nash. And so that ends up becoming a question, is if I'm building a network of agents and they're then I can sort of ask for this particular network, for this particular set of utility functions, then does there exist a Nash, and is it unique? And can I build a solver that will stabilize the Nash? Those are all questions that are kind of downstream from this, but they all start from this definition of a Nash. Yeah?
Is it like only when majority of the others agree with the Nash equilibrium that Xi has to agree with the same, or like?
Well, I don't assume I agree. So again, there's no coordination here. So this is just really, player one is running totally on its own. It can't control any of these variables. And so given that it can't control any of these variables, if you imagine player one is, well, so maybe this will help answer the question, is that for continuous games, then a sufficient condition for the Nash equilibrium, sufficient, is that the partial derivative of u1 with respect to x1 is equal to the partial derivative of u2 with respect to x2, all the way up is equal to the partial derivative of un with respect to xn is equal to 0. So the idea here is that if every agent climbs a gradient, when they settle out at the point where their gradient drops to 0, where they've reached the top of their respective hills, then this is saying that they all are sitting at the top of hills in this space. If I control this dimension, you control that dimension, and so all I can do is look down this dimension, I will climb higher and higher and higher, and I will eventually be at a peak, where if I look this way and this way, it'll be lower. This way and this way, it might be higher, but I don't have control over that. So this is just saying in every dimension, with my utility function in this direction, I'm at a peak. With your utility function in this direction, you'll be at a peak. So if I climb a gradient only in one dimension, and I stop when that gradient goes to 0, and everybody does that simultaneously, then this is an equilibrium of that system.
So, just the last thing, and that is the x star I is the optimal value?
Yeah, the x star, all of these xi's, xi, xj, xk star, are the components of this x star, and that's the Nash. So x1 star, x2 star, you can think of this x star as a vector. So, and then I'm saying, so this we're saying is a sufficient condition.
Or can we also call it as the equilibrium point?
The x star is the equilibrium. So we could say it is a point and it is a Nash equilibrium. I don't want to necessarily, it is in this notion of equilibrium, x star is that. I don't want to call it a generic equilibrium because it may not be a dynamic equilibrium of an iterative system that you've implemented. But so that's the next step, is that how do I build an algorithm that converges to the Nash equilibrium so that the dynamic equilibrium, or the equilibrium of the iterative map, is also equal to the Nash equilibrium. That's another sort of set. But in general, this suggests that gradient climbers can find Nashes. All right. Any other questions about that so far? So this, if you notice, so down here, I'm kind of hinting that in order for you to build parallel numerical solvers, multi-agent systems that converge to the Nash, all you have to do in most cases, and this is, there are conditions that have to be met, but generally in most cases is you just have to have an agent is responsive to its own gradient with respect to the variables that it can control. And under a few set of conditions on the way in which these utility functions relate to each other, then you can get that system, if everybody's just locally following kind of a greedy algorithm, if you're locally greedy, then you end up landing in these Nash optimal solutions. So you just locally do what's best with respect to your little local gradient, and you do what's, and you will end up landing on one of these equilibriums. And on top of that, the Nash equilibrium fits into a much broader set of problems called variational inequalities that basically take this idea and say that these don't even actually have to be gradients. I can actually define these as generic functions, but agent 1 has one function, agent 2 has another function, and so on. And I am either going to be happy with all of those functions equaling 0, or agents being up against whatever their constraints are in a constrained space. And then the question is, can I have my agents find the point that brings all of them to this condition where f1 is equal to f2 is equal to fn is equal to 0. And that's the solution to the so-called variational inequality problem. So it turns out that there are a bunch of problems that have numerical structures that can be decomposed into variational inequalities. And if you can represent them as variational inequalities, you can very easily distribute them among a bunch of agents where each agent is doing the equivalent of following a gradient. And so, parallel gradient climbers are good at finding these types of solutions, these so-called variational inequalities problems. So if you're interested in this area, then I would recommend looking up all of this stuff on variational inequalities and parallel solutions. But the special case of it, the conceptual model, is the Nash. And it kind of makes sense that if you've got a robot following a gradient and a bunch of other robots following a gradient and all of their rewards are coupled together, then if you have kind of the right structure of these different utility functions, then more often than not, they're all going to settle out at the Nash equilibrium. And that will be where all of their gradients are mutually equal to 0. So this is one equilibrium concept in multi-objective optimization. So any questions about that? The definition here of the Nash. And I bring it up just because this is one way to think about merging objectives. And now I'm going to introduce a very different way to merge objectives. This does definitely relate to social systems and natural systems and things like that, because again, the salient feature here is I have a bunch of parallel agents that just can't coordinate. And so that is what this is trying to capture. It is the solution when parallel agents who can't coordinate are thrown into a sandbox together and made to be responsive to their own rewards, but not anybody else's. Question?
I still have a confusion about x minus I star. Can you please explain that?
Yeah, so in this first, this here I would call as x minus 1. I would say this combined with this together is x minus 2, and so on. So all I'm saying here is this is a shorthand notation to say U5, x1 star, x2 star, x3 star, x4 star, x5 star, x6 star, 7 star, 8 star, where I've basically taken that x5 star and for notational convenience, put it as the first argument, and take everybody else and put them as the arguments after it. I've just resorted them so they're all in this ordering, so that whoever is the index here, the variable shows up first. And so all this notation allows me to do is allow me to very compactly say that the decision variable that agent I is in charge of is the only thing I'm considering changing. And all the other decision variables that agent I is not in control of, I'm leaving at the Nash. So the Nash equilibrium is a point such that if you unpacked all of these star values out, they would satisfy this, where the unstarred value here is just an arbitrary value from the decision space. And all of these star values and these star values come from the particular point that we're investigating. Yeah.
When you are taking this partial derivative of, say, player 1 x1, what would be the values of the other players? Will they be random or will they be the maximums?
Well, they're all at the equilibrium. Everybody's gradients equal to 0. Or if you have a constrained space, it's possible they're pushed up against their constraint. But if they're in unconstrained space, anybody can move anywhere. If you've reached the Nash, everybody is sitting at the top of their respective hills. And so everybody's gradients are mutually 0. So that's like dynamically picture this weird space where in one dimension you're so if all of these U values were the same, like U1 equals U2 equals UN equals U, then this is just a multivariate optimization problem like you might solve in high school calculus or maybe freshman year multivariate calculus. So if I was to make everybody's utility functions identical, then this would be the partial derivative of that common utility function with respect to the first variable, partial derivative of that common utility function with the second variable, all of them equal to 0, which would basically mean in my one space, I have one giant hill and I'm sitting at that peak and I look in all directions and I see downwards in all directions. And so what adds to it, with the Nash and then later the variational equality, is it's hard to picture, but what we're saying is okay, player 1 lives in a space that has a hill, and player 2 lives in another space that has a hill. But as player 1 moves around, it also moves player 2 around her space. And as player 2 moves around, it actually moves player 1 around his space. And so how can I guarantee that if player 1 is just following a gradient in one direction, that in player 2 is just following a gradient in another direction, and they're moving each other around, how can I guarantee that over time that player 1 will end up being on top of a hill in one dimension and player 2 on top of a hill in another dimension? So it's not trivial, but that's mathematically what we're trying to depict here. And we're just unpacking, again, it's just multivariate calculus. We're allowing the utility functions to vary in each dimension. Right, so that's one way to merge multiple objectives into one notion of equilibrium. And I've suggested to you ways in which you could imagine ways to find this solution computationally. Mathematically, as I just tried to motivate in my dancing around up here, that it's a very difficult structure to picture. You've got a multivariate, a very complicated multivariate utility function in all of these dimensions, and you only can control your movement in one dimension, and your movement in all the other dimensions just, who knows? So, and so it's not trivial to imagine how this could work, but at least when the variables are continuous, we can use calculus to help us solve this if we have gradient information. So this is in equations and in unknowns. We could solve that. And then likewise, if you had the expressions for these inequations and unknowns, maybe you just invert a matrix, and there are parallel ways to do that. Or an alternative way to solve this in parallel with a multi-agent system is to deploy each utility function and its gradient, or an approximation of its gradient, on each individual agent. And like I said, you could have this robot pays attention to its utility function, this one hers, etc. And then that will tend to, I'm not going to give all of the conditions, but there are certain conditions that allow for parallel gradient climbers to then converge to the Nash equilibrium. And if I can guarantee they converge to Nash equilibrium, and then in the mathematics argue that the Nash equilibrium is a good place for my system to operate at, then I have a way to say, like my grad work was a lot of this. Like I would build, I was interested in load balancing across, say, servers at a web shop or something like that. And I would use these types of methods to say that I didn't need the servers to communicate with each other, as long as I could build some notion of Nash equilibrium into the system that was not that bad compared to the global optimum, and that the global optimum would require a lot more overhead. So I could get rid of all that overhead and show that there was very little so-called price of anarchy. So the price of anarchy is the difference between the utility function evaluated to the Nash and the global utility. And if you can show that there's very little price of anarchy, then you can say that, although I might want to design a fancy communication system to coordinate to get a global optimum, I can get the Nash equilibrium basically for free, and it's not that bad. So that's where the heuristic kind of comes into play. You can use the Nash concept, because it's easy to implement, as a heuristic for finding an operating point of a system that otherwise would require a lot more overhead to find the best operating point on. But you have to justify that the Nash isn't that bad. The Nash might be really bad. So that's a way to make use of this. Yeah.
Apart from that as well, so when I'm climbing in my own dimension, I'm climbing on x1, and x2 is parallelly climbing somewhere, I still need to know how the rope tied between us is affecting me. There have to be some restrictions on that as well.
Well, sure. I mean, there are ways in which, like when I did this sort of stuff with my grad work, in order for me to figure out where I was, I periodically, it turned out I could do this asynchronously, but I periodically would have to find out what was going on over here. But I could temporarily assume that they hadn't moved. And I had to set up conditions of my utility functions and of my communication graph that it would ensure that as long as I was moving in the right direction with old information and everybody else was moving in the right direction with old information, then when I got the updates, I might not have moved as well as I thought I moved, but I didn't do any worse than I started. And then that guaranteed a convergence to that point.
But there is still no guarantee that you would not have done any worse than you started with because you went with old parameters.
Well, that's the thing you try to build into these things, is that, like, I had to prove that there was progress, that the whole system would, as a whole, progress even though it was asynchronous. And you can do that, and there's a lot of work. In fact, Dimitri Boursikis, who will teach a class, who teaches a class right after this one, wrote a book with John Tsitsiklis that is all about this stuff. And how to build parallel numerical algorithms that guarantee that you can converge to things like Nash equilibria, even though you don't have communication synchrony and all that stuff. So it's a huge amount of literature. All right, but I just want to introduce this one equilibrium concept. before we introduce sort of the next way of thinking things, which is a more global way of doing it. So any other questions about this sort of Nash stuff? So anybody seen The Beautiful Mind? How many people have seen Beautiful Mind? So Nash, there's a movie about Nash, and supposedly John Nash came up with this idea when he was in a bar watching people mating off or coupling off and choosing partners. And the thought was that if there was one obvious great partner for everyone, everyone would go with that great partner and nobody would leave with anybody, or one person would leave that one. And so he said, well, could there be an alternative policy that where nobody would regret anything, where you may be partnered off with somebody that wouldn't be your ideal candidate, but would be someone that would be better than nothing. And if everybody was doing better than nothing, and you recognize that everybody was doing better than nothing, then you can't regret it. Like if somebody else took your date, then you can't be upset with the date you got because she or he went with the other person. So that was out of your control. So that's another way to conceptualize this sort of idea. All right. So, but what about other multi-objective problems? So here's an example. So I assume some of you are familiar with a variant of the knapsack problem, and I am going to argue that most of probably the knapsack problem you've learned maybe in an undergraduate course, maybe a course on linear programming or whatever, was probably a heuristic to help solve the more general version of the problem, which goes something like this. So, so in the so-called knapsack problem, the idea here is I've got n items, each of which have let's say a profit associated with them, PI, and a weight associated with them, WI. And we all can agree that it's better to have more profit, and we all can agree it's better to do it with very little weight. And so if I were to sort of plot, if I were to simplify this problem, assuming I could come up with some easy ordering of these things, which, I mean, the whole point of this is that there's not necessarily an easy ordering, but if I were to just compress this down into 2 dimensions, and in one side, I say we'll make total profit, which I guess I can write as the sum of PI for all I in my S set. So I'm trying to choose the set of items S. And then on the other side, I might say total weight. And that is the sum of all the items I've chosen, of all of their individual weights. Now, both of these are going to look something like a 45-degree line, or like a line that is pointing in the same direction. But in the case of weight, it is better to move toward the origin. In the case of profit, it is better to move away from the origin. So I would like to maximize profit, but I would like to minimize weight. And so the question is how do I select which items to put into my knapsack, given that I have this dilemma that if I choose a light object, it may not increase my profit as much as choosing a heavy object. And so this is what I mean by a true multi-objective optimization problem. If you could manage to fix one, it would be an easy problem. But the fact that you have to deal with both makes it complicated to even come up with some notion of an equilibrium. So, so it's sort of a matter of discussion then here. So how would you solve such a problem? How have you seen the knapsack problem solved? Yeah.
How I've seen it before is you take a proportion of the profit and weight. If you're determining which item to add at a time, you see relative to the maybe profit over weight of the items, and you rank them and say, I'll first do that item and then next and next, and be able to.
Okay, so there, and then and how do how do you figure out where to stop?
Usually there's a constraint into how big the knapsack is.
A constraint.
So it's usually, 20 pounds or whatever the amount is, volume of it.
Gotcha. So solution 1 is to impose a constraint. And this is what I call what social scientists would call the satisficing approach, where satisficing is a combination of satisfy and sufficient. And so, so in the satisficing approach, this is one way you basically say, let's say I want to maximize my profit, so I'll define profit as F of P and define weight as F sub W. So maximize profit subject to the constraint that my weight is less than or equal to some W max. And so this is a constraint provided, and I'll say, by stakeholder or something. And so this now turns a complicated problem into a relatively simple problem. So I can come up with strategies to solve this. I might be able to write this as a linear program. There are solvers for linear programs. This might be easy for me to do. Worst comes to worst, I just can enumerate the space of all possible things that I could put in my knapsack, exclude all the ones that are too heavy, and then I can, then of the ones that are left over, of the ones that aren't too heavy, I pick the one with the biggest profit. This is one way to solve that. Yeah?
How is it more complicated if we don't have the constraint?
Well, if we don't have the constraint,
We can take everything. Doesn't matter.
well, that's the thing, so how do you, so the problem with the constraint, which I'm trying to get at here, is how do you choose this max, this W max? So if I don't have a constraint, then the question is like, so imposing a constraint is me saying that I kind of value, that this sort of is an assertion of my values. I don't actually care about minimizing weight. I just care about maximizing profit, but I have some reason to believe that if it gets too heavy, I can't carry it out of here. And so I'm suggesting that weight is important to me so long as it is beneath a particular constraint, or so long as it is not above a particular constraint. If it is beneath a particular constraint, I forget about weight. So if, for example, the power set, or if, for example, the entire set of items, if I add up all their weights and it's under this constraint, I don't even worry about that objective. It becomes a single objective problem. So this is a subset of the more general knapsack problem, and it is a simplification because we have methods to solve this thing pretty easily. But the problem is somebody has to give us this weight. And then it's like a hyperparameter. How do you decide on this weight? So you could say, okay, well, I'm going to set up some, so those of you who've taken optimization 1, we might have learned about the Krush-Kuhn-Tucker conditions and Lagrange multipliers. And if you haven't, that's fine. But basically, to solve a constrained optimization problem like this, you can assign effectively a price called a Lagrange multiplier to every constraint. And you can then tell somebody that if you wanted to increase the constraint by a certain amount, this price term tells you how much additional benefit you'll get by increasing the constraint a little bit. So in potential, by solving this problem, I could come back with somebody and say, here's kind of the cost of imposing a constraint. And that kind of gets closer to what we actually wanted. So, and ultimately that's what we're going to get to an equilibrium concept that is more explicitly that way, but that's one way to do it. What might be another way that I could come up with a solution to this problem that's not imposing a constraint?
Pareto Frontier?
We'll get to that. That's what we're building to. Can you define a Pareto Frontier?
Can I define it?
Yeah.
It is, if you were to take both maybe number or profit on one side, or one axis, and
we'll see what we
Kind
mean
of,
by
right?
optimal. Yeah, we'll get to
Yeah.
that's what we're all building up to. Yeah.
You could just brute force through the power set of all these items and see which one gives you the lowest weight and the highest profit.
The lowest weight and the highest profit. So, but which one which? Like I could see the set that gives me the lowest profit,
Yeah.
or the highest profit. I could see the set that gives me the lowest weight. But how do I combine those two? How do I find the one that's somehow in between?
Maybe make it,
This whole program is.
maybe we can form an equation where they are inversely proportional to, I mean,
Inversely proportional. What do you mean by that?
like if the profit gets like higher value, the weight gets lower.
I see.
And then when we make an equation and form, like, try to maximize that equation.
All right. So that I think we're getting to something that I refer to as scalarization of this problem. Is the other common way to deal with this. And it's this basic idea that I can decide, if I were to go back here, that weight is so much important versus profit. I can somehow come up with a way to say that I care about minimizing weight, but I care about maximizing profit a little bit more. And so can I turn this into a simpler problem where, let's say I want to maximize my profit with a discount factor for my weight, and this here is a scalar that I have to then, is again provided by stakeholder. And so this is a way for me to say that if I really don't care about weight, I set that thing equal to 0, and I'm just going to be a profit maximizer. I don't care what the weight is. If I really, really care about weight, I set it to infinity or something, basically infinity, and that effectively turns this thing to 0. What you could also do is make this a convex combination. So this could be 1 minus sigma, and this could be sigma, and sigma could sweep from 0 to 1. And so this is a way for me to balance these things and turn 2 optimization objectives into 1. But again, the question is, who decides what that value is? So there's a level of subjectivity that I don't like as someone who is being asked to insert myself into an application area that I may not have the domain knowledge in. So I need to ask somebody else to specify that, but they might not know how to exactly specify that. So if I just choose an arbitrary value, then, so it's hard for me to say what to choose there. So one option is I could choose several of those, and I could say, you may not know what value, what scale you want here, but maybe I'll show you it for 0.1, for 1, for 5, for 50, for 5,000, and you can look at all of those solutions. And that's going to get close to where we're talking about with this Pareto Frontier that we're coming to here. Now there's one other way that I could solve this problem of dealing with these two. Anybody else guess that's kind of the third way that we could go with this? It's viewing it less as a maximization and more of a minimizing loss function type of perspective.
We might know the best value of the weight and the best value of the profit, and we can take the difference, square it, and sum out.
Exactly right. So that's the third way you see people deal with these. I would view this also as a sort of another scalarization perspective. Is to build targets. And so the basic idea is somebody comes to you and they say, you got this knapsack, and ideally we would like this much profit, and ideally it would be this much weight. And maybe you combine these things where you say ideally it'd be this much profit, but we don't want it to be any more than this weight. So you basically set up a target, and you could do something like, let's say I want to minimize this profit with respect to some profit target, but then I also have this weight with respect to some weight target. And the alternative to that would be, maybe I want to maximize this quantity. So both of these are sort of targets. This is sort of saying, I really want to hit this profit target, and I am totally happy with going over that. But I really need to be under this weight target. And so that is a way of combining these two things together. Yeah.
Is this similar to goal programming?
Well, this is, yeah, the same sort of idea here, and again, there's variations on these you can basically combine, and my claim is, if you really want to turn this into a scalar problem, like not this kind of vector objective, a single objective problem, you're going to probably use one of these three methods. Or you can imagine injecting a weight in right here, or right here as well. So instead of being just least squares, it becomes weighted least squares. So, but those are three different ways to say, here is a way for me to give you one solution. And my claim is that there is an alternative that I think in most cases is a better alternative, where you don't give them one solution, you give them a set of solutions, and you let the stakeholder decide from that set. You don't have to force them to give you a value of this scalar or anything like that. You just say, here are a bunch of solutions that you're not going to regret, not in the regret like Nash equilibrium regret, but maybe that, I don't know. But the idea is you're generally saying that nobody is going to, you're not going to come back, nobody's going to sue you for making these choices. Although there's a set of choices that we'll identify that they would have grounds to sort of say these were bad choices. So how do we come up with ways in which to combine objectives that we somehow don't regret? And so that's where we're entering into this, this area of Pareto optimality. And it is my claim that multi-objective optimization and Pareto optimality is super well suited for evolutionary algorithms, because evolutionary algorithms make use of a population. And these solutions to Pareto optimal problems are sort of naturally fit to have populations of answers as opposed to one answer. And so what do I mean by Pareto optimality? So let's, I'm going to get more general, so not the knapsack problem anymore. So I'm going to say I have two objectives, F1 and F2, and I will just plot them. Maybe they're both are in terms of a single x. And just to put them all on one plot, I will plot F1 going up and F2 going down. And so let's say that F1 looks a little bit like this. It had kind of a slow start, and then it's got this kind of peak, whereas maybe F2 is a little bit quicker start, it's a little fatter, but then they both end up ending in roughly the same place here. And so the question is, if I would like to maximize both of these things, so I'm going to say that it's good to be higher in, or good to be in whatever direction you want to call this. Say it's good to be higher in F2, which I've plotted going down. It's good to be higher in F1, which I've plotted going up. And so I would like to be at the top of both of these things, but I can't be, because the top of this one is over here, and the top of this one is over here. So I have to make some trade-off. That's the big term here, trade-off. And so, so the question becomes here, not where should I be, but where should I not be? So can anyone identify ranges of x values that are definitely bad choices?
To the left of F2,
So,
yeah.
so I hear left, so like over here seems bad, right? And the other tail, I heard tails, over here seems
A
bad.
little bit on that one, there's a
Right.
little bad side on that.
So somehow I want to be in the middle here.
Right.
And so we want to make, so if I were to, if you're, you're sitting there, you're writing a paper, it's a framework paper, how would you make that a little more quantitative? For this graphical example, how do I define these three regions? The bad region, the good region, and the bad region. How would somebody out there do that?
Their relationship to the maxima.
What do you mean by relationship to the maxima?
So if your gradient has gone down in F1, and you've noted that the point where the gradient is 0 in F1 occurs after F2, like we can see that, but if you determine that mathematically and you notice it starts going down, beyond that, that's bad. And then you notice we happen to know F2, the gradient equals 0, occurs before F1, so to the left of that would be bad.
I'm just trying to sort of summarize here. So the idea is, so the maxima, there's gradient stuff in there, but I don't think we necessarily have to get that deep here. But I think this idea here that, based on the maxima, these maxima define these areas, because what we're saying here is that this region over here is a region for which, if I were to pick any point in this region, it would be better for me to pick a point farther over. This is what we refer to as a Pareto improvement. So if it improves all the objectives simultaneously, it's a Pareto improvement. Yeah.
So to answer your question, you define a partial ordering on each, like, on the set of like solution vectors.
Yes.
Where one is like better than the other if none of its elements are less than the others.
Right, and that's we will unpack that statement a little bit more. Actually, in the next lecture, when we actually go down to how we build algorithms that find this, because we need some notion of a gradient that is defined in this weird space, and we need a type of ranking, and that ranking is very much the partial ordering that you're referring to. So yes, very good insight that we will be seeking a partial ordering, and for those of you who don't know, just we'll get there. So, all right, so this here, so again, I'll put that term up here, Pareto improvement. And that means that it is a change where all objectives are improved. And we can contrast that with a so-called non-dominated solution. So a non-dominated solution is one where there is no way to make a Pareto improvement. So no Pareto improvement possible. So if I were to put that another way, I can say that if for any point in this box, the point to the right of it dominates that point because it is improved in both dimensions. Similarly, if I were to go on the other side here, any point here is dominated by points on this side of it. Because for this point, if I just move a little over, then I go up in both. So if you're a decision maker, I can't tell you what the best trade-off between these two things are. That's subjective. But I can tell you, you should not make a choice in this box or in this box. And that's Pareto optimality, defining the set of solutions for which you cannot be called an idiot. So no idiot solutions. So nobody can blame you for making a choice here. This is that thing like, he chose this solution and he might have chose the solution next to it, but I can't blame him. These are the no blame solutions. They're like, he made a tough choice. In his perspective, profit was a little bit better than weight. It may not have been my choice, but I can't blame him. Now, if you're over here, they're like, wow, if that idiot would have done something differently, then he could have had more profit for less weight. I can blame him for that. That was a dumb choice. So these are the things we want to avoid. And so we want to build tools that identify the things that somebody can come at you and say, this is bad because you could improve in multiple objectives simultaneously. And so these solutions in between here are referred to as the Pareto-efficient set. And it is a notion of optimality. If I was to go back and define this in a kind of Nash perspective, then what I would say is that you are a point in this set if the only way you can make an improvement in one objective is by making a decrease in the other objective. So I could go back and rewrite the Nash equilibrium type of, the same sort of thing where I've got U1 and U2 and the X minus I star. I could do all of that in the Pareto case. But what I would be saying is that if there is an improvement, it has to come at a cost. And so that means there must be a trade-off. There is no trade-off here. There's no trade-off here. We want a trade-off because that means that we are living on the edge. We are living in the good spot engineers love trade-offs. If there's no trade-off, there's no engineering. We want to find the trade-off space, and that's what the Pareto efficient set is. So no Pareto, because there are no Pareto improvements, it's efficient. If there are Pareto improvements, it's inefficient. We say in economics that the market has reached an efficient solution if the only way somebody can make more profit is if someone else makes less. So we arrive at the market solutions are supposed to be Pareto efficient, and that everyone has arrived at a point where no one can do better uniformly. Somebody's got to do worse. If we live in a society where we all could do better, we all should just do better, because it's inefficient, and that's what we're capturing here. Now I could plot this in a different way, where I put f1 of x on this axis and f2 of x on this axis. And if I were to do that, I can see that f2 reaches a maximum when f1 is pretty close to a minimum. And so I can imagine that if I said, like, this is the maximum value for f2, then I know that the point that joins the two of these is going to be one where, even though f1's max is out here, in order for me to get f2's max, maybe I have to be, say, right here. Likewise, f1's max, right here, f2 is not at its max, it's nowhere near its max. So I could plot another point where at f1's max, f2 is taking quite a hit. And I could go through and I could define a set, basically I could sweep through all the x values here, and I would end up carving out a space that might look like this. And these are all of the feasible solutions. So like you can see, there is a solution where they both are basically 0. That does exist out here. There are a set of solutions that are infeasible. And a boundary between the feasible set and the infeasible set is the so-called Pareto Frontier. And so this is the Pareto Frontier. And so the solutions along, it's basically the image of the Pareto efficient set in the objective space. So if you take all of the solutions that are right here, and then you project them into all the objective values that they map to, you end up getting this thing here, and that's the Pareto Frontier. And that is something that if I can provide this Pareto Frontier to my stakeholder, that is far more valuable to them, because it captures in one image, just this line right here, this is the trade-off between the one thing that you like and the other thing that you like. If you really want speed and you really want accuracy, we can build solutions along this whole curve here. You have to tell me where. Just know that for every little bit of speed you give up, you're going to get this little bit of accuracy up. So the slope of this line is far more interesting to me than any particular point on this line. If this line is basically flat, or if it is shaped in a particular way that's flat most of the way and then becomes steep, then I know that, oh, in the flat parts, I don't have much of a trade-off. So in the flat parts, I don't have to give up much of this objective to get more of this other objective. If it's a 45-degree angle, then that tells me that pretty much there's a one-to-one mapping between what I have to give up in one to gain in the other. So the slope and shape of this line is far more interesting to a decision maker than any particular point. And that's why we would like to build algorithms that, given an arbitrary set of objectives, will find this reduced manifold and produce this manifold for decision makers to choose upon. Doesn't require them to choose a sigma value or anything like that. But every point along this manifold, at least I would say a sufficient condition, but not necessary, to be on this manifold is that scalarization problem where I said, let's say I want to maximize, I'll do 1 minus, say this, f1 plus this times f2. If I choose sigma values from 0 to 1 and solve this optimization problem for all of these values, each solution will correspond to a different spot on this line. So if you have a set of convex optimization functions and you want to know the shape of this line, one solution is to solve this maximization problem for a wide range of sigma values. And you will then, every solution will end up walking down this line. Question, yeah.
You were able to reduce this into a two-dimensional manifold only because there are two parameters right now.
Right.
If
Well, not two parameters, two objectives.
Two objectives, yes. If we had, what would we have done?
Yeah, so I mean, the idea is you typically have fewer objectives than you have decision variables. So usually you have like, you might have 1,000 decision variables and 3 objectives. And 3 objectives, that would be a 3 space, but then the manifold here would be 1 less than that, a 2 space. So basically, optimization is the process of reducing the dimension of your objective space by 1. So normally I give you 1 objective and you give me a point out. So I've gone from a 1-dimensional space to a 0-dimensional space. Here I've given you a 2-dimensional preference plane here, and you've reduced it to 1 dimension for me, this line. If I gave you a 3-dimensional objective space, you would give me a 2-dimensional out. So it's still a hard problem to say, well, how do I choose that? I don't have a way for you to do that unless you give me this subjective criteria. So this point is minimizing subjectivity. So you came at me with 3 objectives and a whole bunch of subjectivity. I come back with you with effectively a 2-dimensional manifold, but no subjectivity. So how do we get rid of the subjectivity in our problems? And that's really what we need to do as data scientists when we have stakeholders come to us. They're going to come to us with all their baggage. We want to find a way to take all the good stuff out and put all the baggage aside. And that's what these Pareto optimal criteria are supposed to do. Yeah.
Yeah, so with something similar to dimensionality reduction, do you have something of the sort for objectivity reduction as well? Like you use something like a PCA to decide what gives me the most variance and get rid of the rest?
Sure, I'm sure you could do some sort of feature selection-y sort of thing if you do study a lot of multi-objective stuff, then what you'll find is there'll be certain objectives. This almost gets there are ways to turn objectives into constraints. So, and then there are ways to ask, when I'm meeting one constraint, when do I automatically meet the other constraint? And that sort of deactivates the objective. And so there are kind of notions like that. And I would claim that you kind of have to go back to one of these sort of solutions, like the target solution or the constraint satisfying one, to kind of get there. But there are sometimes ways to go directly from a multi-objective problem to a single objective problem with multiple constraints. But it's not trivial. It's kind of outside the scope of this discussion. But certainly, if somebody throws at me 1,000 objectives, then yeah, I think there are definitely ways out there to say that, if you think of this Pareto Frontier, imagine that you can imagine that this Pareto Frontier is going to be a multi-dimensional manifold, but it might be flat in between a lot of those dimensions. And so you basically say, you know what, it doesn't matter how you choose these things. What really is, where are the trade-offs? And you find the strongest trade-offs when you say, well, what is the slope along this manifold in sort of, let's say, just to make it easier for humans, in every plane. Imagine every way I could cut the plane through this and see where the highest slope is, and maybe that's what I present to my stakeholder as saying, this is really what you should be considering. But absolutely, there are definitely ways to do that outside of the scope of this class, but I think that's good thinking. Yeah.
You said that line would represent if we have a convex optimization problem. What would be the case for non-convex?
Well, I guess what I was saying here is that this is a sufficient condition, and in order for me to guarantee that I find that if I solve this, I find the whole frontier, then I kind of am limited to these convex functions. But so there are a certain set of optimization criteria that if you did this, like you can imagine weird shaped Pareto frontiers that maybe have like weird bubbles in them or something like, they can't quite have, but there's like a shading effect. But but you can imagine gaps that if you solved this, you might miss this gap. And so we do need more general solvers that are able to find those. But in quite a lot of the problems that are formulated, this solution would be a way to trace out the whole Pareto frontier. So any question about this framework or this general idea that now we've gone from producing one solution to producing a subset of solutions on which there is a trade-off. We're effectively eliminating solutions for which there is no trade-off. And we would like to build an algorithm that will generate this for us. And so my claim that we'll investigate as we move into the next lecture is that an evolutionary algorithm is great for this because you've got a population that can converge not on a point, but in principle can converge on a line. So you run your genetic algorithm, and if you've adjusted it just right, then you should get a population which starts maybe all the way down here, and as it moves, it gradually moves up closer and closer to this line, and then just packs along this line, so that it ends up producing an approximation of the line. One of those challenges is the fact that we don't know where that line is, so how are we going to build agents that move toward the line? And this goes to this partial ordering. How do we define a partial ordering where we don't know where kind of the bottom of that order is, but we know that we're getting closer to it? And that's something we'll have to figure out how to do. The other problem we have here is the diversity problem. In the one objective case, we only worried about mutation producing diversity because we were interested in the exploitation-exploration trade-off. We had maybe two local minima. We weren't sure which one's better, and it was the global, and so we needed enough mutation to search the space and then settle down into one of them. But we ultimately wanted to settle down. Here, how do we maintain diversity and yet do so in a way that we don't just constantly be scattered here? So we want progressive movement closing this dimension while we actually want radiation in this dimension, and we don't know what those dimensions are. So we need to discover radiation dimensions and convergence dimensions as we go. Yeah.
Give non-dominated solutions a much higher chance of becoming parents.
That is the so-called Pareto ranking. That's effectively what it's going to do. Is so that's kind of the beauty of if we could come up with one metric of domination, refining, coarsening this problem into something that has multiple realizability. So we have one metric, and I don't care what you're dominating, but I care that you are dominating. Then that allows us to put pressure on these solutions in this direction while allowing them to be free to move in this direction. And so that is exactly where the kind of, I would say, the second generation of these Pareto optimizers went to. The first shot at these evolutionary algorithms to solve these problems, which I'll start with next time, basically was motivated by this thinking. You had a bunch of people who took a linear programming course and maybe a programming course and knew a little bit about biology, but not that much. And then they created a genetic algorithm motivated by this expression. And there were sort of two ways to do that. One of them was sort of directly motivated by this. The other one was kind of motivated by this idea of what if I run a GA on one and then run a GA on the other, then run a GA on the other, and then come back. And so those were two ways to sort of produce diversity here. But then somebody had your insight later on, and they said, wait a second, let's throw this whole thing out and come up with a way to rank solutions in terms of how they dominate other solutions. And that provides us a way to provide progress in one direction, but not squelch progress in the other. And then as we get into these more complicated things like multimodal optimization, whatever, then people added the ability to create like niches and even additional diversity, because even if you're not compressing in this direction, you still want to, that's the trouble, is like dealing with not converging in this direction is one problem, but then how do you also spread in this direction? So I need to be agnostic to this dimension in sometimes, but also be very aware of it in other times. So how do I get uniform spread across this dimension? And that will be the problem that we'll sort of discuss. And there's, NSGA2, for example, as I think one of the most, and I think there's actually an NSGA3 that is one of the leading, and I think 3 now, is one of the leading multi-objective genetic algorithms, which has Pareto ranking, but also diversity, and that's all about how do I introduce a Pareto ranking and also maintain uniform diversity. And so this is still an active area of research. All right, well that's all I've got for you today. Happy to take questions after, and we will get into the concrete details of how to build these algorithms the next class.